Now, from with this new information, you now look at this. This denominator is relatively prime to P, and it divides the product of P and another integer. So that means it has to divide that other integer, where we are using this condition. This result, if A divides BC and A and C are relatively prime, then A divides D. If A divides BC, where A and C, suppose you consider this as C, if A divides B times C and A and C are relatively prime, then A has to divide C. And so, if I want, I can give reference to those exercises, but you get the point from where I am getting these things. And hence, and so, this divides P minus 1, P minus 2 to P minus K plus 1. Okay. So that means what? This quotient, this divided by this is an integer. In other words, this binomial coefficient is P times an integer. Okay. And thus, or I can write like this, thus P minus 1, to make it more clear, is an integer. Okay. This implies P divides this binomial coefficient. That's what we wanted to prove. That's what our claim was. And our claim has been proved. Now we go back to the expansion of the term of the expression using binomial theorem. There we encountered these coefficients, right? So this, which is equal to a to the power p plus PC1, a to the power p minus 1 plus PC2, a to the power p minus 2 plus etc. plus PC p minus 1 a plus 1. Okay, now all these terms are divisible by p because the binomial coefficients in them are divisible by p. So this is congruent to a to the power p plus these terms will become 0 plus 1 modulo p. So this is nothing but a to the power p plus 1 mod p, which is congruent to. Okay, now what is our induction hypothesis? What was that? Keep that in mind. Our induction hypothesis was that a to the power p is congruent to a. So in place of a to the power p, I can write a plus 1 mod p. So you see this, a plus 1 to the power p is congruent to a plus 1 mod p. So this is the induction step. We have completed the proof induction here. We have proved the result for a plus 1 based on the assumption that the result is true for a. So this completes the induction and the solution. Okay, so that completes the first asterisk exercise. There are 2 or 3 more. Let me just quickly go through them. Exercise 15. If m and n are integers that are relatively prime, then given again 2 integers a and b, prove that there exists an integer x such that x is congruent to a mod m and x is also congruent to b mod n. This is a special case of something in number theory that is called the Chinese remainder theorem. Okay, we will see that at one point. So here there is a very slick solution. I don't know why I seem to never remember the solution. Okay, it starts with this condition, of course, because that's the only thing we are given. Since m and n are relatively prime, there exist integers say k and l such that mk plus nl is equal to 1. Then, okay, you look at this one, b minus a times km plus a, this number, this integer. What can we do here? Km, in place of km we can write 1 minus nl and we multiply b minus bnl minus a plus anl plus a. So minus a and plus a cancel out and this becomes, let me continue from here. So these two cancel out. We are left with b minus bnl bnl plus anl, or we can write b minus, actually what am I writing here? X is congruent to a mod m, so x has to be congruent to n, okay, plus a minus b n l. So this number, this integer and this integer are the same. Now take x equal to this one, b minus a km plus a, which is also equal to a minus b n l plus b. Then x is, okay, then what do we get from the first equality? X minus a is divisible by m, because b minus a times k is an integer, or in other words, x is congruent to a mod m. Look at the second equality, x is equal to this, then x minus b is divisible by n, because a minus b times l is an integer, and that means x is congruent to b mod n. That's what we wanted to show, right? So there is such an x. So it's like solving two simultaneous linear congruences at once. X is an unknown quantity. Suppose you think of it like an ordinary equation. Ax is equal to b, something like that. Okay, and cx is equal to b. It's a system of two simultaneous linear equations. Suppose you want to solve this just like that. You can have two simultaneous linear congruences, and that can be solved provided this condition is true. This thing can be generalized to give us that result, which has the name the Chinese remainder theorem in number theory. Okay, then we come to exercise 16. So this solution ends here. Prove the corollary to lemma 132. We have already proved this there itself when we stated the corollary. There itself we have proved. So for us this is already done. And is this the last one, or there is more? No, this is the last one. 17th one is the last one. Prove that in again a condition which says that an integer is a prime number. Prove that n is a prime number if in Jn this equation implies a is equal to 0 or b is equal to 0. In Jn mean, by that we mean that these are congruence classes modulo n. If the product of any two congruence classes is equal to 0, and it implies that one of the congruence classes has to be the 0 congruence class, then n is a prime. So let's now solve this and finish this set of exercises. Okay, so this is the condition given to us. But instead of directly proving this, if this happens, then n is a prime, we prove the contrapositive. If this does not happen, then n is composite. Okay. Oh, sorry, that's not the contrapositive. Sorry. That is not the contrapositive. If n is not prime, then this does not happen. Yeah, that's what we will prove. So assume n is not prime, then by now we already know what we have to write here. Then n is equal to AB for some, then n has a non-trivial factorization for some A and B satisfying these inequalities. Okay. So n divides AB, but n neither divides A nor divides B. We have already seen why in this case n does not divide A and does not divide B. Because if we assume n divides A, then n becomes equal to A, because A also divides n. In that case, B will be equal to 1, which contradicts this inequality. Similarly, n does not divide B. However, n divides AB because AB is nothing but n itself. In terms of congruence modulo n, how can we write these relations? Or in other words, AB is congruent to 0 mod n, A is not congruent to 0 mod n, and also B is not congruent to 0 mod n. Hence, since AB is congruent to 0 mod n, so what will be this product? This is nothing but AB, congruence class that contains AB, which is equal to 0. But similarly, this is not equal to 0 and this is also not equal to 0. So here what we have proved, if n is not a prime number, then this is not true. This is not true for all A and B. There exists at least some A and some B for which this is false. This equal to 0 does not imply that we must either have one of them equal to 0. That's not the case in this for this particular A and B. So negation of n being a prime implies negation of this, or in terms of contrapositive, or whose contrapositive is this statement, that if this is true, then n is a prime. So that's why the solution ends here, and this completes the set of exercises that is there at the end of section 1.3, which is called the integers. So with this preparation, we are now ready to start ring theory, that we will do in the next set of videos, and things will keep coming. If you are new here, please subscribe to my channel and like the content if you like it. Even if you dislike it, you can dislike, you are free to do that. It's better if you give some sort of feedback in the comments. So looking forward to having more discussion like this with you. So that's the end of all these things for now. So I am the caretaker signing off from this mathematical room. Have a nice night.